Afternoon, thanks for coming. This is my talk, Stealthier Attacks and Smarter Defending with TLS Fingerprinting. Nominee for the award for the least funny title at DerbyCon ever. The other equally unfunny but true title is the Zero Math, Almost Zero Crypto TLS talk. If you are after some kind of DJB teardown of elliptic curves with calculus and stuff, you're probably going to be disappointed. I don't do the big math thing. But if you want protocol analysis and that sort of thing, then hopefully this is more for you. The agenda is really to do a quick TLS primer for people that aren't up to date on what TLS really is. If you are, it doesn't matter, it's pretty quick. I'll do a little bit on TLS fingerprinting as a whole, do a little section on attacker and defender scenarios, and then give you some tools so that people can go and play with this stuff themselves. Before we start, I should mention I use HTTPS a lot as an example when I'm working through these things, but it's not an HTTPS talk. It applies equally to other TLS enabled protocols. This is really just because everyone understands browsers pretty well, so it's an easy example for most people to grasp. The other thing is when I talk about various signatures and what you can do with them, none of these are hypotheticals, they're all been done. So if I say you could fingerprint app X, I have already fingerprinted app X. It is possible, it's not just a lab type scenario. So with that said, a quick TLS primer. TLS is what we really mean when everyone says SSL. And if you really mean SSL, you should not be in this talk, you should be at your office getting SSL out of your environment, moving to TLS. And then you can watch the recording and then catch up on this. But people use TLS encryption as a phrase as if it's an algorithm, and it's not an encryption algorithm. It's a protocol used to determine which cryptographic algorithm, amongst other things, you're going to use. It's great for fingerprints because it doesn't get mangled by NAT, proxies, firewalls, or anything. It's completely payload-based. It doesn't use TCP headers or IP headers, so it doesn't matter what your networking equipment does, it stays intact, unless it's being man in the middle. So the most common use is HTTPS. You've got a browser and a web server and they want to talk to each other. And that would be fine if you just had one browser in the world and one web server in the world. They could have a predefined set of crypto algorithms they use and use them, but that's not the case. The web server has to interact with more than one type of browser. And so they need to find a common ground in what their capabilities are. And this is predominantly what TLS offers. They exchange their capabilities and determine the best one that they can both use. Similarly, there are other web servers in the world, so the clients need to be able to adapt to what server they're talking to. When you visit a website, you don't know in advance what web server it's sat on, so they constantly have to negotiate for each connection. And of course, there's plenty of other browsers that make this more and more complex. And as you start seeing from the diagram there, it gets a mess of different possibilities and different options, even just using the mainstream browsers. There's no old browsers in here, there's no old versions of these browsers, there's no command line stuff, so you can imagine the number of permutations there must be. So how does it work? Well, you click the Use TLS box, crypto fairies appear, they sprinkle magical crypto dust, everything becomes secure, eavesdroppers and government surveillance go dark, dystopian future is avoided, and we can all go home, have a nice drink and chill out. Unfortunately, the reality is slightly more mundane, and what actually happens is you have an exchange of hello packets whereby the client and the server explain to each other, for want of a better word, what their capabilities are, what cipher suites they support, what compression they support, that kind of thing. There's a key exchange, which is shockingly exchanging keys, cryptographic keying material, and there's options to change the cipher spec partway through so they can renegotiate different settings. And then you've got the encrypted data. So what from this is useful to us? Well, we're looking at TLS clients. So really stuff from the server is kind of pointless. We don't want anything encrypted because, like I mentioned, I'm not DJB and I can't do anything clever with encrypted data or math. And we don't want the client key exchange because the key, if it's done properly, is going to be unique to a session, so it's pointless for fingerprinting, which only really leaves us the client hello packet, which is really convenient too because that's the first packet you ever get in a TLS transaction, so you can fingerprint at the earliest possible opportunity in the session. So, SSL primer out the way. Let's actually talk about fingerprints. So first of all, why clients as opposed to servers? Well, servers you can actively fingerprint. You can connect to a server and probe it and determine what the server is. You can't with a client, because by default, it's a client. It's not listening. You can't prod it. You have to wait for it to be prodding something else before you can determine what it is. Secondly, a server announces what it is anyway. If anyone's ever connected to an SMTP server, a web server, anything like that, they just scream the software that's being used across the banner. There's no real need to fingerprint. Servers are always the same. You connect to an Apache box, and the next time you connect to it, it's still an Apache box. You don't really need to determine things on a per-connection basis. If you're attacking a client, you don't know if a user's going to open IE or Firefox or Chrome, so you don't know one TCP connection to another what it is. Even if you've profiled them once, that doesn't matter 2 seconds later. And finally, because of this, servers are much more configurable than clients with regards to TLS. If a server has been modified, then it no longer matches a fingerprint, so they're much more difficult to fingerprint from a TLS perspective. Clients, however, don't get modified as often. How many people have logged into their browser and actually removed supported cipher suites? Actually, in this room there probably are some, but there are not many people generally that obsolete cipher suites from their browsers. So, let's get to where this started, and hopefully that'll illustrate where I'm going to with this. Back earlier this year, or end of last year, Lenovo bundled Superfish. Well, they got busted again today, but they busted they bundled Superfish in with a bunch of their laptops. And PrivDog was out there that was meant to be helping with SSL, but was actually man-in-the-middling SSL. And there's been a bunch of other tools that were all discovered around the same time. And everyone was worrying about them. And we had headlines like this, which was talking about how the certificate had been dropped onto people's machines in various ways and had been installed as a certificate authority, allowing the app to go and re-sign connections as their own, and then people went and cracked that certificate and could sign whatever they liked as that certificate authority and attack those clients. But the certificate was only part of it. You could see other things that the application was doing. With my hardcore hacksawing tool of Netstat, you can you can look at the processes. You can see that there are 2 processes that talk to each other entirely on localhost. And then one of those processes goes and talks to the internet. Now, if you look at what those are, it's process number 4084 and 3388. So, using my other leet hacksawing tool of Taskman, you can look at 3388. That's Internet Explorer. That's the one talking on localhost. The one hitting all the websites is client.exe. That's because what's happened is, and in this case it's a tool called GeniusBox, same sort of thing as the others, is the client.exe has, through one means or another, either hooking connections, updating the browser's proxy settings or whatever, has told it to connect to it, and then it connects out to the internet. You can also take a hint when you look at its install directory that it might be doing something with TLS. It's got things for making certificates. So we know it's doing something with TLS, and we know the browser's connecting to it. And the browser isn't getting errors because, like Superfish, it has a trusted certificate in the CA store. And that means that it can re-sign anything it wants. What that also means is that no traffic from IE is hitting the internet. It stops there at the client. It's not forwarded, and the client makes its own connection out. That means that whatever occurs on the network from an eavesdropper's perspective is purely that of the client and actually nothing to do with IE. So if we take a packet dump of an uninfected Lenovo laptop and an infected one and put them side by side, we can see that they're not the same. Even a cursory glance. They support a completely different number of cipher suites for a start. The preferential cipher suite is a completely different one. They're not even using the same version of TLS. So they're pretty distinct from each other when you look at them side by side like that, and that's on the same machine. That means that you can derive a fingerprint. These are in a bunch of offsets in the TLS header, and I can go and look for them, which I did. I wrote a snort rule that could detect this stuff on the wire. It's useful for system admins because a system administrator doesn't necessarily have access to the endpoints. We're in a world where people can bring their own devices in, and the enterprise doesn't necessarily have access to look at that device. You may not have access to the server end. So really, you don't have an idea as to whether someone is Superfish infected, for example, or any of the others, without having access to the endpoint. But by sniffing it on the network and alerting on Snort this way, you can detect it using your existing infrastructure. Even this guy, whoever he is, seemed to be quite impressed with it. So let's expand a little bit, because that only works so far. That rule I made only worked on the Cypher suites. The problem is that if you look at Cypher suites, Chrome version 45 and Firefox version 37 look the same as each other, and they both look the same as Thunderbird version 38. So you start to get collisions. In fact, of the first 150 signatures I collected, I would have only had 75 unique ones if I'd stuck with Cypher suites like I started. So we need to look a little bit more at what we can do with the client hello packet. So this is a standard header from a client hello. It doesn't represent the sizes of the boxes, don't represent the size of the fields, but it is the ordering. So this block here is fixed location. You can find it really easily with no computation. They're at the standard offsets from the beginning of the payload. This section is mostly fixed-ish because it depends on the size of the session ID. But once you've calculated the session ID, then it's an easy offset for these. And extensions you actually have to parse properly, because extensions each have a length of their own, and you have to find the length of an extension, hop to the next extension to find the length of that, to hop to the next, and so on. So that's a slightly more CPU intensive, but it's still not that bad. So what's useful in here? Well, we don't want to use any of these length identifiers because we know the length. We've got the data already. Those are just there to navigate the packet when you're grabbing it from the wire. We do not want to do the session ID, because the session ID is shockingly unique to the session, and we really don't care. And random is, well, it's random, so again, I don't care. The extensions are really useful. The extensions add a load of extensibility on top of what's already inside TLS. For example, there's a server header that puts the host name that you're visiting in the clear, in case you thought that was secret when you're browsing to a website. And that's to allow the hosting of multiple websites on a single IP address, each with their own SSL cert. It can determine the cert before you get to the crypto, it can present the right cert, and that way you can do the equivalent of the jump from HTTP 1 to 1.1, the V hosting but with SSL. Also, being able to check the order of things is incredibly important, so we log those in the fingerprints too. Extensions load in a different order for different browsers. There is no RFC defining the order you load them in. Similarly, the cryptographic algorithms are listed in a preferential order. The compression algorithms are listed in a preferential order. So by logging the order, not just the capabilities, we get another level of granularity on the fingerprint. So let's actually talk about creating a fingerprint. Well, I needed to get some sample data, so I sniffed a few of my own clients and made the fingerprint. But I needed to get a bit more data than that. So I realized there are websites out there who are dedicated to doing regression testing for web developers. You write a piece of CSS and you know it works in the last 30 versions of Firefox and 20 versions of Chrome or whatever, but you don't know what it's going to work on other than that. So there are services that will go and fire 30, 40, 50 browsers at your website. They all take a little JPEG screenshot and they email them to you so you can see if you wrote some horrible CSS that broke Firefox 2 or something. The great thing about that is they have completely honest user agent strings. So I can point them at my web server that's sniffing absolutely everything and correlate the fingerprints I generate against the fingerprints, against the user agents provided, and I've instantly got like a whole bunch of fingerprints I can use. Fingerprints I've been storing are like this. This is Dropbox. There's nothing particularly special about Dropbox in this case other than it's the shortest fingerprint so I can get it on a slide easily. But I've been storing in JSON. It's fairly human readable. There are a bunch of libraries to parse it. Things like Python do it natively, so it's really useful for people to use and to transform into other forms. The server name is in there, not because we use it for fingerprinting, because that would just get us back to a situation that's like blacklisting, which I'll come to in a minute. But the fingerprinting tool I wrote stores the server name purely because when you've generated a ton of fingerprints and you're trying to work out which goes with which client, this helps you piece it all back together again. Also, I'm worried about deobfuscation. I don't know all the TLS-enabled protocols. There's the obvious ones like HTTP and IMAP-S and SMTP-S and whatever. But there are plenty of protocols out there I don't know. So I want to be able to spot TLS on other ports. Also, if anybody has ever worked in a large corporate environment, you will know this command. the one that uses the universal firewall bypass port to get at your personal box so you can do what you want on the internet instead of going through the company proxy. And this just illustrates my point, that people are not looking for SSH on port 443. In fact, they're largely ignoring 443 because it's just encrypted stuff. Hackers don't listen to IANA's guidance on port numbers either. So if you're exfiltrating data, they're not necessarily dropping it straight on the port you think it is. Blocking FTP may not be enough. So my goals are to detect TLS traffic and fingerprint it on any port, to do it completely statelessly, because tracking TCP sessions and that sort of thing can be quite intensive computationally. I want it to be asymmetric, because we talk about large networks these days, so I don't want to have to see both halves of the conversation. And I want it to be fairly low cost in terms of CPU, memory, and storage, and I'll come to the storage thing in a minute too. By keeping all this low, we should get higher detection rates, more accurate detection rates, and not need quite such the hardware to drive it. So, to detect TLS on any port, we kind of need to fingerprint TLS as a whole before we move into apps. So, this is a BPF filter. Anyone that uses TCP dump or snort or something will know these. But it's 2 checks on 2 bytes. The first one checks that it is a packet that identifies itself as a TLS handshake packet, and the second check checks that it's a client hello within that. That gets a pretty high rate of detection on its own, but we can get a bit better. We check this 1 byte here, and it's the first byte of a 2-byte value for the TLS version. If the first byte is set to 3, that will get you all TLS ever, because the various versions of TLS, as in 1.1, 1.2, use the second byte to differentiate. So this one gets you all TLS. The bit in blue is if you're a masochist. That gets SSLv3, and that's just horrible. I would rather recommend alert on SSLv3 being in your environment, panic about that, and don't put that in this. And then we do the same again for the TLS record version. By just checking 4 bytes, with no horrible offsets to parse, so no CPU computation, that gets you right down to pretty much detecting TLS as a whole on every port. Your only real CPU bottleneck is going to be being able to drive the network card fast enough for the overall packet filtering to apply the filter. You can also shrink your throughput down further by adding a 5th check, because there is a byte for the session ID length. If the session ID length is 0, i.e. there is no session ID, then that means it's the first packet in a TCP stream. So you only capture 1 packet per stream as opposed to the subsequent renegotiations. And that way you can trim your storage right down and just get 1 packet to examine per stream. So of course, just remove the blue because we don't want SSLv3. That's the filter you want to apply. And it's pretty low CPU cost too. To talk about storage and retention, the reason I mention storage is that if you want to get use of this, this is one of those things where you probably want to harvest data all the time and then go back and analyze sort of signals intelligence style if you can, because if you have an event happen, you might want to look at what happened yesterday, TLS-wise. So I did some analysis to see. I've taken mixed traffic. I took a ether tap and tapped 4 gigs of inbound and 4 gigs of outbound from my home network. So it's mixed traffic. It's TLS traffic, it's iPads, it's, whatever, a whole mix of things. And can it determine it? Because actually downloading binaries from HTTP is one of the biggest ways to trigger false positives on this, I found. So, how well does it do? Well, unfiltered, 99.226% of packets were useless. So, that sucks. Implementing that first check gets it down to just under 3% being useless. The third check, as you can see, 0.005%, and I had a 100% success rate with no false positives when I implemented all 4 of those checks. That's not to say it's ironclad, but in that 8 gigs of data, I didn't have anything, and in subsequent tests too, I haven't got any false positives. Additionally, it saves on the storage. That 8 gigs of data, when saved to PCAP with that filter, went down to 20 megs, which compared to 8 gigs is not much data. If you implement that 5th byte check to only look for the first packet, it becomes 5.4 megs. That's what, like 4 floppy disks for 8 gigs worth of data fingerprinting? Which I don't think is particularly bad going. So moving on. there are a couple of flaws that are worth discussing before we get into the beef of actually looking at it. One is that obviously people are going to think modifying my own fingerprint to evade this is a sensible technique. And obviously it's possible because the client controls its own client hello packet. There are a couple of gotchas, however. To modify your fingerprint, you have to modify the hello packet. And to modify the hello packet means that you are announcing a different set of capabilities to the world. If you're announcing new capabilities, you have to be prepared that the server on the other end is going to call on those. So you need to actually have those capabilities. Similarly, if you're removing some to make sure they're not in the fingerprint, that could cause you problems because you may be lowering, say, the cipher suites that you use to a weaker level. Additionally, if you're using a library as opposed to coding your own TLS interactions, it may abstract a lot of this from you. You can choose cipher suites most of the time with libraries, but I don't see many that let you choose the order that you load your extensions in, for example. The other thing is fingerprint collisions. So if two clients look exactly the same from a fingerprint perspective, they cannot be differentiated when you're analyzing them because you can't tell which it is because it has the same fingerprint. And the definitive answer on whether this happens or not is sort of ish, maybe, kind of. Because what happens is I did get multiple fingerprint collisions where I couldn't differentiate two clients from each other. But then I noticed that although they were the same fingerprint in different apps, under the hood they were the same thing. So if you look at apps, particularly on cellular devices, you have multiple apps that will have the same fingerprint. But then you'll find that what's really happening is they have embedded WebKit in each one. So it's actually, from a technology perspective, it is the same client. And that's important because they are the same client in terms of what they're vulnerable to, what they're not vulnerable to, which we'll come to in a second. But if they're vulnerable to the same things, then from an attacker's perspective, I don't care that they're different clients. From a defender's perspective, you maybe care a little more, but you can still differentiate them from IP addresses and things like that a little bit more easily. So let's get to examples, because that's way more fun than me waffling on about this stuff. Let's talk defender stuff. Anyone that does defense in a network has probably seen lists like this. You spend forever exporting flow stats, firewall logs, proxy logs, and end up with pairs of IP addresses that are talking to each other. You probably have an idea about the connections, and you may even be monitoring some clear text protocols, but a lot of the time you don't really know what these connections are. One of them might be suspicious, so you might go and TCP dump it on a packet sniffer. You can see it's port 443, and you can see that it's a big garbled mess inside. So the only possible conclusion is that it's probably your user's web browsing, and what can you do? You can man in the middle it or something like that to try and determine the content, but most people are not doing that. You could do it with keying material derived from the client or the server to decrypt the packets, but again, you probably don't have access to those. You could check against IP blacklists. This is some data that Alex Pinto provided, and if you want more data and a more sane review of this, watch his talk, it's awesome. But this is the rate of change of data in blacklists. Each of these bars is a day. You can see that blacklists do not remain static, they change every day. If your blacklist is not updated as often as the published blacklist, you are probably out of date. This also includes data being removed from blacklists, so you might be incorrectly flagging things. Similarly, you don't know how long before things appear on a blacklist. So, whilst they are useful, you can't guarantee that you're catching everything this way. The thing I like about the TLS fingerprinting is that people don't tend to update how their crypto is set up that regularly. Even the big browsers with their regular releases have the same crypto between versions a lot of the time. And when I looked at malware, it never really changed its crypto signatures. Oh, and blacklists don't include internal traffic, of course, either. They only look at things like botnet control and command and control bot servers. So let's look at that list again. You probably do a few things, look in whois, look at DNS records, and you can determine what a bunch of these are. Some of them might scream bad, the unknown connection to an SSHD, the IRC session. But what about this host, 1054.103.99? You can see it has what appears to be an HTTPS session to SharePoint and an HTTPS session to Amazon Web Services, which says nothing because the entire internet's on Amazon Web Services. How about if you TLS fingerprint it and see that it's actually MITM proxy that's connecting to SharePoint? Maybe this is someone attacking another client on your network, man-in-the-middling the connection, and grabbing the documents or the credentials as they go past. What about the Amazon Web Services? Well, if you fingerprint that as a Tor uplink to the Tor network, maybe that's data being exfiltrated that they're just pulling off SharePoint. With some context, this makes things a slightly different view. And there's anomaly detection, in quotes. For people that have a really controlled environment, you can work this the other way. You don't just detect things that you think might be troublesome. If you have a corporate image and everyone uses one version of one browser all the time, or just a couple of browsers, you can have fingerprints for your known corporate tools that everyone uses. Anything else? Presumably bad. You don't even need to think about what it is. You then get flagged which client you should be going to look at, and you can go have a look. From a defender's point of view, it's not just about all the hacking. You don't need to be looking at hacking tools and picking them out. There are a couple of other things on your network you probably don't want to see. Like that. Java, for example, has a fingerprint when it goes to update itself from the web server on the internet. Also, any app you wrote that's compiled in Java will have the Java fingerprint. So you can spot someone using Java. If you have an environment where you have outlawed that because it's horrible, then you can spot it. You might have tools that are against corporate policy. Despite being fine in their own right, you may not want them in your environment depending on what it is. You may have tools that you just don't want to talk to the internet directly. There are the really nice security tools that are great in the hands of your security team, but when they come from your finance department and are pointing at a box, you're probably less pleased about them. You probably also have things that you expect humans to interact with. So when you start seeing scripts interacting with them, then that's probably a sign that you've got some kind of issue you need to address. And all these signatures are in the database that I'm going to give you at the end here. So, attackers are normally man-in-the-middling when it comes to TLS, because passively doing something with TLS doesn't do a whole lot. There's a bunch of ways to get in the middle, and it depends on who the person is. So it depends where they are, how well funded they are, technical capabilities, that kind of thing. Your ISP is in a very different place to man-in-the-middle you, as opposed to someone who's on your network doing ARP spoofing, for example. Then you can do the whole, oh my god, nation states and BGP hijacking and all that stuff. There are a bunch of ways. But either way, they're getting in the middle and are actively intercepting traffic, modifying traffic, blocking traffic, whatever. This list is not exhaustive, but it does give you a flavor of the different ways. So what are the attacks on TLS? They largely clump into three groups. You can attack a client that's known to have weaknesses, so the client doesn't check certificates. It has certificate chaining issues. It supports weak ciphers that you can crack, whatever. There are attacks against TLS libraries and frameworks. They have coding issues. They have buffer overflows, whatever. They do not check things properly. Things like Heartbleed, where there's bounds checking issues. I know that's a server, but it's the easy example. And then the other one is CA issues. Your client's fine, everything works fine at a technology level, but it trusts a CA that's rogue or been hacked, and so a rogue certificate would still be effective against that client. The enemy of the attacker is, of course, the perfectly functioning client that flags up a big error saying someone's attacking me and raises the alarm. This is what we're trying to avoid, especially in many of those man-in-the-middle situations where a single person hasn't been targeted. There's wholesale man-in-the-middle against the entire network. If you're pen testing a desktop LAN and you man in the middle of the whole desktop LAN, you're going to get a mix of clients. You don't want that coming up and setting off the alarm. Unless you're a defender, then you do want that coming up. So, let's look at a standard Windows host and see what we can do. Sorry, no, that's not a standard Windows host. Let's look at a standard Windows host and see what we can do. So, what does this user do? Well, we can see that this user has a few browsers. I don't know one URL to the next which browser is going to be connecting. If I have a Chrome vulnerability and I drop it on Firefox, I'm going to get an alert. That's not very stealthy. So, I need to drop it on the browser that I want. They also have a bunch of other tools on this box. These tools all create TLS-enabled sessions, and that's, they could be things that I want to avoid, they could be things I want to attack. And this is just from a random screenshot I found on Google Images. There's a bunch more on most people's boxes. So, bearing all this in mind, here's the example. Google reported that there was a CA that had gone rogue, I guess for want of a better word, that it was issuing certificates that should not be trusted. They issued the warning, and so they pulled it from Chrome, as you would do, to get the advantage over other people. So in this situation, I'm knowledgeable of this, this attack, and I want to attack people, but I don't want to attack Chrome, because Google have just announced to me that they're going to set off alerts when I do. So, I have the client, I'm man in the middling, through whatever, DNS spoofing or ARP spoofing or something. The client does its TCP handshake with me. Great, I don't have to do anything with that, I just maintain the handshake. They send a client hello packet to me. I run my fingerprinting. It's Safari. Safari is on my known bad database. So I just work like a port forwarder. I do a TCP handshake of my own, forward the client hello packet on to the evil server, and then just pass packets backwards and forwards. And that can be whatever I want. It can be an existing tool like MITM proxy or Metasploit or whatever else I'm using to attack it. And it can be on localhost. But then the next connection comes in and it fingerprints as Chrome. So I forward it to wherever it was connecting to originally, because I have the destination IP address, because that's in the IP header from when it connected to me. This way I can remain stealthy, because the Chrome user never hits my exploit and never flags it up. I never see this. Instead, I see this. This is a little port forwarder I wrote. All it does is it listens for connections and forwards to a different location dependent on fingerprint. It saw Chrome and sent it to the real Google. It saw, what did it saw? It saw Safari, and it sent it to the real Google. So let's look at the next offender example. You can do fingerprint-defined routing. That's pretty much the same as what I described just now, but from a defensive point of view. Same again. I place something in front of my servers, much like a reverse proxy. It gets the handshake, get the hello, and then I see that my server, that's expecting humans to come and look at it, gets a connection from Golang. So I throw that at the honeypot. The honeypot can gather whatever intel it wants about what this person is doing, and my real server doesn't get touched by them. When I get a Chrome connection, however, that gets sent to my real server. The pages get served and everything works. So the next attacker level, anti-forensics. The scenario is, I've already looked at my targets, I've prepared all my exploits, I'm ready. I know who I'm attacking in the network, and I may even have dropped a first stage bit of malware, I may have sent a phishing link, but essentially what I've done is I've set myself up so that to bypass the corporate firewall, I'm waiting for the data to connect out from the network to me, and I'm listening. Meanwhile, back inside the organization, the sneaky security defender guy has spotted the URL, and they're using the standard tactic of using wget with a modified user agent to appear to be IE7 to come grab the sample malware off my box. Which works a lot of the time, because generally you can't tell. But if you host your malware on an HTTPS box, so it's TLS enabled, you can forward a wget signature to a seemingly innocuous server, and you can send IE7 to your attack server, and therefore the defense person and malware analyst doesn't have their sample and doesn't know that you've dropped that stuff. And then on the defense side, you can do fingerprint canaries. We have homogeneous platforms these days. People like Netflix and applications like FaceTime and BlackBerry Messenger, they manage their entire infrastructure so that they own the servers, they own all the API endpoints, and they write the application. It may not be on their infrastructure, but it's their app. They don't have third-party apps. So if you run a network like this, you could have a fingerprint for your app, because you know when the fingerprint's going to change, and you know what the fingerprint is. You don't necessarily have to do anything about it, but when you see a different fingerprint come in, it could be someone man-in-the-middling it. It could be someone attacking you, deliberately man-in-the-middling themselves, using something like Burp Suite, for example. Or it could be a customer being man-in-the-middle. Either way, you could detect it, and you could react to it and deal with it. And of course, no talk about man-in-the-middling and attacking would be complete without the oh my god nation-state attackers are coming after us. And some of that might be useful to them. Even if they're not man-in-the-middling things, there's useful operational info. If they see that you're a Skype user or use a particular IRC client or something, it may give them something useful to go and tap for further information. Some apps are only available on one OS, so that signature tells them what OS you use for some other attack. If they see that you are using a particular gambling app, they might infer that you have a gambling problem that they could go and blackmail you for. And in fact, today in the press, there was Karma Police came out, where the UK GCHQ were analysing people's porn habits, amongst other things. By looking at this, you get a lot more information, and if you're doing wholesale interception like that, you could essentially determine a lot of information about people. And an honourable mention goes to honeypots, for if you're doing the, I don't want to use the word, but threat intelligence. If you put your little vulnerable WordPress install on HTTPS instead of HTTP, you don't just know what vulnerability someone is exploiting, you know what they're exploiting it with. So if you're looking at groups and attribution, being able to say that this group not only used this exploit, but they did it from some Ruby script, probably says a lot more than they just use CVE, whatever. And even unknown fingerprints are good, because the same unknown fingerprint would mean reused code base, most likely. And if you look at any of the attribution stuff that's gone on with malware, reused code is a pretty common thing. So you could do a certain amount of attribution just from the fingerprint without actually looking at what they did on the box. So, let's move to tools, because tools is the fun stuff. That stuff's all good in a lab, and it's great for me to talk about it, but it doesn't really help you guys do anything. So, I'm releasing a couple of tools for people to use. First one is Fingerprint TLS. It's a, shockingly, packet sniffer / PCAP file reader. If you don't want to trust my tools running on a network, you can capture them your own way, throw it in a PCAP file, and throw it at this. It does that cross-port TLS detection stuff. It will log match signatures like you can see on the screen. It's got a bunch of things saying there's a Tor uplink, there's MUT, there's Thunderbird, whatever, talking to these hosts. It'll log the server name and pull it out the TLS header for you and tell you what it was connecting to, not just from DNS, but from the actual host name, which gives you a lot more idea about what it is. So that's hopefully useful. The other one is I wrote Fingerprint out, which is just a Python script, but it takes that JSON file and it outputs it in a number of different ways that's useful to you. This is a C struct, so if you write C code, and it's probably changeable to other languages that I don't know, you can use it to put fingerprints in yourself. So apps can self-fingerprint incoming connections. This was a fingerprint of Shodan, who kindly scanned my box whilst I was packet sniffing. But it worked out quite nicely, because now I know what all their nodes are when they keep reconnecting. The next one is an IDS output. It's a suricata and snort output. This is probably most useful to people, because if you have existing IDS infrastructure, you can use this to push signatures out, and you don't even need to run any code of mine. You can have your IDS alert you when you see specific things that you don't like the look of. It's a bit funny looking, because most IDSs don't have support for the various fields inside the SSL stream. So I had to derive them myself. So you've got all these distance and byte jump things to actually manage all the offsets and get there. This is actually a pretty short signature. Some of them are a little bit long. And if anyone tries this and has issues, if you're using Snort, take a look at your main config. It likes to pre-mangle SSL, so it doesn't look like it did by the time it gets to the rules, which is so helpful. And the final output from this one, oh no, second to last. Is there anyone from Signal Intelligence here that's submitting it? No? Okay, well. If you were to admit to being in Signals in SIGIN, I did X keyscore output so that you can go and attack everyone on the network too. It's actually the least reliable of the signatures. I don't know what that says. The one last thing I did do with it was to perform data sanitization, because when you do your fingerprint, it stores some of your personal data in there, like the server you were connecting to. So you want to strip that out before you go and publish it to someone else, rather than it being in your sample. The other thing it does is dedupe. And that's kind of good and bad, apart from when I saw this. The Wayback Machine bot archived my machine. Yay! It matched the same as Java. Boo! I kind of had a ragey flip out, like, moment, because I thought I was getting bad fingerprint collisions were coming my way, and I'd gone down like a bad rabbit hole on this. But it turns out, thanks to the marvels of GitHub, that it's actually written in Java, and I had completely correctly fingerprinted it after all. Woohoo! So, This brings it to one nice other little point, that you can use this to determine the lineage of apps. Compiled apps less so, but scripted stuff and certain things like Golang and Java that are sort of in the in-between area have very specific signatures. I've also got signatures for PHP, for Python, for Ruby. It's very useful for being able to determine when someone's attacking you, not just what they're doing, but what they're using to do it. It can give you some more clues. Finally, I'm releasing the fingerprint database itself. It's far from comprehensive, but it does have a lot of things. It's probably got about 150 signatures in the main file, which includes browsers, email clients, some WebDAV connections, IRC clients, a gambling app, Java, GNU, TLS, and a bunch of other stuff. There is another file that's about 250-ish signatures long that I separated out. If you've ever used the SSL Labs certificate checker, it throws some ridiculous number of tests and generates 250 unique signatures. You may want to exclude that, that's why I've separated it, but if you're interested in when people are scanning you, that might be of use. So we get to the demo that inevitably fails because it's a demo and it's going to fail. So I was going to do an attacker demo. I was going to show you the two Googles, and then I thought, well, this is the fix-it track. It's defensive more than offensive, so you don't want that. Besides, watching two Googles not error is not really a very exciting demo. So what I actually did is, for the duration of this talk, I've had a listener running on this machine on port 443, and I've been running my fingerprinter on it in the hope that some malicious person is scanning the network and I can fingerprint them scanning me, and that can be my really exciting demo. So let me just break out of this for a second and find the no. Sorry, let me just sort out my desktop. So, okay, so what you've actually picked up is my laptop in the background connecting out and doing a bunch of things, as opposed to people fingerprinting me. But that would have shown really leaked things in there if they had been, because it's got detection for things like Metasploit and stuff. Just to show you how it works, I'll create some data. So if I was to curl the HTTPS interface of Google, then you see up here it matched curl pretty quickly. And yeah, it does it for most other clients. Let me just put this back. Am I back? No, I'm not. Now I am. Okay, so that's my failed demo. I'm glad I predicted that with the Windows error screen. So, what's next? I'd love to hear back from the community on stuff. I would love if people wanted to contribute signatures, check things out of GitHub, fix my awful code and make it better, fork it and do a cool thing, whatever. Or help write new tools. I would love to see this as like an Apache or Nginx module or something like that to treat clients differently natively instead of having to use sniffers. So, if anyone wants to be involved, this is where everything is. The tools I just showed are all on the GitHub repository. It's all Python or C. There's some Twitter accounts if anyone wants to interact with me. These slides are on SlideShare. And the blog post down the bottom is like a mini white paper that outlines the technical details of this without me waffling on and giving silly examples and everything. Some random observations wrapping up. OpenSSL S client defaults to SSL to v2 for some reason, which explains why I couldn't see it. That's horrible. The most popular extensions being used are elliptic curves and signature algorithms for the elliptic curves, which is why those are two of the extensions that I deal with differently. Which I neglected to mention. I do a load of parsing on extensions too. You'll see that in the technical write-up, sorry. And the other thing is, everyone, when Snowden released all the stuff that he did, said about never trusting NIST again. NIST P256 and NIST B571 curves account for 98% of the preferential curves seen in all clients I've seen. So all this don't trust NIST stuff doesn't seem to have filtered down to the clients. It still seems to be fully trusted. Anyway, that is what I had. If anyone wants to ask any questions, that'd be great. I'm here all con, so feel free to stop me. Otherwise, thanks. Which one, sorry? Oh, the links. Yes, there we go. Thank you. Appreciate it. I did.